Welcome to Tomorrow Unveiled, the deep dive into the innovations that are reshaping our world right now. This week, we are focused entirely on just the dizzying pace of robotics development, specifically that pivotal week of December 8th through the 14th, 2025.
Mhm.
And this wasn't just a week of cool lab demos or, some conceptual proposals. This was the watershed moment. This is where the industry's narrative decisively shifted from, look what we can do in a test environment, to, okay, how fast can we sign the checks and deploy this at scale? Physical AI. And by that I mean the convergence of these highly advanced algorithms, robust foundation models, and a working mechanical body. It officially became an industrial asset category this week. Right alongside forklifts and automated storage systems, we've been provided with an absolute mountain of research for this, covering everything from massive investment announcements and, profound financial strategy shifts to specific algorithmic breakthroughs coming out of top labs like MIT and NVIDIA. Our mission today for you is to extract the most critical cross-corroborated insights from all that material. We are going to get you completely up to speed on why this week signals the true institutional rise of the machines.
It's fascinating because the structural shift we observed, it's really being driven by a convergence of three things: capital, market consolidation, and algorithmic maturity. For the better part of a decade, the robotics industry, especially for humanoids, was kind of stuck. They were in what insiders called pilot purgatory, just endless small-scale tests, custom-engineered solutions for every single customer, high failure rates, and just enormous uncertainty about scaling. But this week, we officially entered what we're calling the infrastructure era, and that's a structural shift. It proves that the underlying technology is now reliable enough, and maybe more importantly, insurable enough for institutional money to treat it like a long-term, predictable asset. The financial strategy, in a way, has matured even faster than the mechanics. Our compiled data and financial sources, they all noted this consensus prediction that general-purpose humanoids will capture, and I'm quoting here, large sections of low-skill, high-turnover factory work in the next 5 to 10 years.
Oh, that timeline used to feel so speculative.
Exactly. But the deals we saw this week proved that the capital markets are now betting on that timeline as an absolute certainty.
Okay, let's unpack this with the hard numbers, because the scale of commercial validation is, without a doubt, the biggest corroborated news of the week. This is what signals the final, definitive end of the research phase and the concrete beginning of the mass deployment phase. I mean, we're talking about deals measured not in dozens or even hundreds of units, but in the thousands. So first up, the massive agreement that fundamentally changes the sales model for robotics. I'm talking about the deal between 1X Technologies and EQT Ventures. This is a deployment agreement for up to 10,000 NEO humanoid units.
10,000.
Right. EQT plans to deploy these units across its vast global portfolio of over 300 companies between 2026 and 2030. It's impossible to overstate how much of an order of magnitude shift this represents for a robotic startup.
The size of the deal is astounding, yes. But what's far more revolutionary is the mechanism behind the deal. We're now calling it the portfolio deployment strategy. To understand this, you need to remember the historical struggle of these companies: sales friction. Robotics involves selling highly complex, high capex, that's capital expenditure hardware assets. A traditional startup would have to spend months, sometimes years, just to convince a single manufacturing client to buy 10 or 20 robots. That whole process involves custom engineering, lengthy regulatory hurdles, high customer acquisition costs, and, often high failure rates during the initial implementation. It's just slow and incredibly financially taxing.
So how does EQT get around all that friction?
Well, EQT acts as a super customer, or in financial terms, a centralized leasing authority. They aggregate the demand across their entire ownership portfolio, which spans logistics, traditional manufacturing, retail, even parts of the healthcare sector.
Right, from all 300 plus companies.
Exactly. So by making one massive purchase order for 10,000 units, they give 1X immediate, enormous manufacturing certainty. 1X can now optimize its supply chain, its production lines, knowing it has guaranteed delivery targets for the next 4 years. But here's the financial acceleration part. The robots are now being treated not as hardware you purchase outright, which hits the company balance sheet as CapEx.
Right, a huge one-time cost.
But as a leased, operational expenditure or OpEx asset. This is crucial because, CFOs are far less intimidated by manageable monthly OpEx leasing fees, which are immediately comparable to or often lower than human labor costs, than they are by a massive one-time CapEx purchase. That shift in financial structure is what really accelerates the displacement of manual labor in these low-skill, high-turnover roles. The economic comparison becomes immediately compelling.
That makes perfect sense for mitigating financial risk, but what about the technical risk? If EQT is leasing 10,000 units, what happens when their portfolio companies start reporting, say, a 20% failure rate? Who takes that risk? Does 1X just get shielded from all of that?
That's the real genius of the portfolio deployment strategy. The risk is aggregated and distributed across hundreds of companies, so it mitigates the impact of any local failure. EQT can manage this risk internally, setting up centralized maintenance, replacement schedules. For 1X, they're shielded from that traditional warranty exposure because their primary customer is EQT, who is essentially taking on the system's integration risk.
So 1X can just focus on making the robot better.
Exactly. They can focus purely on refining the hardware and software performance, guaranteed by a stable revenue stream. This model is why we're calling this the infrastructure era. It's about financing long-term, durable assets.
And the Neo Humanoid itself. This is signaling a strategic pivot for 1X, right?
Yeah.
Away from its original vision. They originally marketed this as a lightweight consumer home Android. Now they're prioritizing controlled industrial environments. Is that a massive step back, or does the industrial setting fundamentally solve some kind of engineering roadblock?
Oh, it solves a massive roadblock. And that roadblock is the sheer chaos of an unstructured environment. The home is the final frontier. It's unpredictable. The lighting is varied. People leave obstacles everywhere. There's high liability risk. It's a nightmare.
Right.
The industrial setting, fulfillment centers, light manufacturing is far less chaotic. It allows 1X to refine their perception models and their control policies in monitored, semi-structured environments first. And beyond that, the NEO's design is actually ideally suited for this industrial pivot. It's because of its patented, tendon-driven, muscle-like actuation.
Muscle-like actuate.
Yes. Unlike rigid, gear-driven industrial robots, this actuation is compliant. It enables safe human-robot proximity, which is non-negotiable in modern manufacturing, where robots have to work side by side with humans, not locked up in cages. Its lightweight, bio-inspired approach is a strategic safety differentiator that allows it to slot into settings like hospitals or food production lines, where heavy, rigid robots are just impractical.
So while 1X is tackling the private equity world, we saw Agility Robotics securing dominance in logistics with a major commercial agreement. This one is with Mercado Libre, often called the Amazon of Latin America. This deployment is for their bipedal digit humanoid, and it's starting in a massive fulfillment center in San Antonio, Texas.
This partnership is so significant because it validates the specific premium value proposition of bipedal robots over, say, wheeled carts or even traditional robotic arms. The core argument for Digit is what we term its brownfield advantage.
Brownfield.
Think about a typical older warehouse. It was designed for human workers. It has stairs, narrow aisles, cluttered areas, and standard shelving that requires a vertical reach. Traditional autonomous mobile robots, or AMRs, those are the little wheeled devices, they require a warehouse to be completely purpose-built or undergo a massive, costly infrastructure redesign.
That's a greenfield deployment.
Right. Digit, by being bipedal and human-sized, can operate seamlessly in those existing human-designed brownfield facilities. It can climb those stairs, navigate those narrow clearances, and reach objects on high shelves without the need for expensive structural overhauls. This ability to integrate into the world as it currently exists is what makes it a massive accelerator for adoption.
And the cost of redesigning an existing, say, 500,000 square foot warehouse can run into the tens of millions of dollars. So Digit essentially allows you to skip that entire expense.
Precisely. And its readiness for this isn't theoretical. Our research team cited corroborating data that Digit has already completed over 100,000 tote-moving tasks in live commercial environments.
Wow.
So that's successfully picking up, moving, and placing those plastic bins over and over again. That number isn't a lab benchmark based on simulated time. That is proof of commercial readiness and real-world robustness at operational scale. And that verifiable milestone puts enormous pressure on every other humanoid competitor still struggling in the lab to provide real, quantifiable commercial data.
Okay, so the third major development in the commercial arena wasn't about deployment, but industry consolidation. And it was shocker. SoftBank Group acquired ABB's robotics business for approximately $5.375 billion. This acquisition effectively removes one of the traditional Big Four industrial players from independent operation.
And if we connect this to the bigger picture, this is SoftBank enacting its artificial superintelligence, or ASI, strategy on a massive scale. SoftBank is fundamentally a software and chip company, right? Through its ownership of ARM and its massive AI investments we're about to discuss. ABB, on the other hand, provides the physical industrial iron, the reliable, precise, high-volume robot arms that underpin global manufacturing.
The workhorses.
Exactly. They are the workhorses of the automotive and electronics industries, often caged, but immensely valuable for their sheer installed base. So what SoftBank aims to do is inject its advanced AI chip design and sophisticated software expertise directly into ABB's existing hardware base. This is the ultimate techification of industrial robotics. Before this, SoftBank was trying to build its own physical presence. Now it has leapfrogged that entirely by buying a dominant, proven platform. The robot arm is no longer viewed as just dumb, specialized hardware that repeats coded movements. It's being redefined as an intelligent endpoint in a massive computing fabric.
It sounds like a vertical integration strategy. They're controlling the entire stack from the chip arm to the brain, their AI investments, all the way to the hand, which is ABB's installed hardware. Does this threaten established players like Fanuc and KUKA? I mean, they've traditionally relied on hardware precision.
Oh, absolutely. It changes the competitive landscape overnight. Fanuc and KUKA are legendary for their mechanical precision and reliability, but they are generally less sophisticated on the core AI front. SoftBank is essentially saying, we can take ABB's already reliable hardware and overlay the world's most advanced, adaptive AI software and proprietary chips. This move signals that the core competitive advantage is shifting decisively from mechanical engineering, how fast and precise the gears are, to software and intelligence.
How quickly can it learn?
Right. How quickly can the robot learn a new task and adapt to disorder? SoftBank is moving to close the loop, to own the physical mechanism that executes the commands generated by its ASI models. And that fundamentally challenges the old guard.
The competitive advantage is software. You've made that very clear. And this is where it gets really interesting, because we're transitioning from the body and the capital structure to the intelligence itself. The consensus across all the sources is that the brain is rapidly becoming more valuable than the body, and the valuations certainly bear that out. Case in point, the massive rumor, which was corroborated by multiple financial sources compiled by our research team, that SoftBank them again, showing their ASI commitment, and NVIDIA are discussing a strategic investment. Over $1 billion in skilled AI.
Incredible.
This deal would value the company at a staggering $14 billion. That's nearly triple its previous valuation just 6 months ago.
This valuation really raises a critical question for anyone watching this space. Why is a company that doesn't manufacture a single robot body and hasn't announced a single large-scale hardware deal worth $14 billion? And the answer lies entirely in its product. Skilled is building a universal brain. See, historically, robotics has suffered from chronic fragmentation. If you bought a Boston Dynamics Spot quadruped, you needed its proprietary control system. If you built a custom industrial arm, you needed bespoke control code. Every new robot body required a new, custom-coded control system, often written completely from scratch. Skilled is aiming to abstract away the specific hardware. They're building a single foundation model, a massive AI trained on data from all forms of robotic interaction designed to control any type of robot, regardless of its morphology.
So quadruped, wheeled, humanoid?
Any of them. A manipulator arm. It doesn't matter.
So if Skilled succeeds, they become the Windows or Android of the robotics world.
Yeah.
They provide the operating system, and the hardware manufacturers just build the shell.
Precisely. They become the single point of intelligence that unlocks scalability for everyone else. The high valuation suggests that investors believe the OS for robotics, that foundational software layer, will yield vastly more long-term value than any single physical machine itself. If Skilled can successfully create a single, agnostic AI system that handles perception, planning, and motor commands, they solve the core scaling problem for the entire industry by creating a standardized platform for intelligence. That level of market control absolutely justifies the valuation.
And the company that literally provides the cerebral cortex for so much of the AI world, NVIDIA, also released details this week on their new dual-system framework for robot reasoning. They're calling it ThinkAct. And it's designed specifically to tackle the Achilles heel of current autonomous AI, long-term, complex, multi-step planning.
Right. To understand ThinkAct, it helps to use the analogy of human cognition, famously divided into System 1 and System 2 processing. System 1 is fast, intuitive, reactive. It's what makes you catch a ball instantly without thinking about trajectory.
Your gut reaction.
Exactly. System 2 is slow, Analytical, thoughtful. It's what makes you plan your taxes or plot a cross-country road trip. So NVIDIA has structured their robots' decision-making in a similar way. They use a high-level, multimodal large language model. That's the reasoning stream, or System 2. This is the abstract planner. It handles the big picture. It receives a complex goal like, go into the kitchen, find the blue mug, and put it next to the coffee maker. And it breaks that down into logical, human-like steps. The execution, that's the System 1, it's handled by a separate lower-level policy. This is the immediate reactive motor system that executes the specific physical commands, like moving a joint 3 degrees, or applying a specific torque to grasp the mug, or adjusting its balance while walking.
The challenge then has to be connecting that abstract high-level plan from the LLM to the precise physical movement of the motors. How do they bridge that massive gap without requiring years of physical testing for every new scenario?
That is the core technical breakthrough here. It's called the visual plan latent. Think of the latent space as the robot's imagination. When the System 2 LLM generates a plan, it doesn't immediately send motor commands. Instead, it generates a compressed internal representation of the visual outcome of that plan. It hallucinates what the scene should look like after the action is complete.
So it visualizes success before it even moves.
Precisely. It essentially visualizes, if I move my hand this way, the cup should land here, and the scene should look like this. It then compares this simulated visual latent state to its current real-world perception. If the simulated outcome looks correct and successful, then and only then does it execute the low-level motor command. If the visual plan latent suggests failure, for example, the cup will likely fall, it aborts the movement and regenerates the high-level plan.
It thinks before it acts.
It literally thinks before it acts, and that dramatically reduces catastrophic physical errors and increases the success rate in complex, long-horizon tasks that require reliable memory and planning.
And that ability to simulate internally before committing to real-world movement is a game changer. It must save time, computational power, and hardware wear and tear.
Oh, absolutely. And that simulation capability is amplified by NVIDIA's update to its general-purpose foundation model, GRU0T N1.5. It demonstrates improved zero-shot transfer capabilities.
Okay, zero shot. What does that mean in plain English?
It means that a task learned entirely in a virtual environment in simulation using Isaac Sim can now be successfully applied to a real-world robot without requiring extensive, costly, and time-consuming physical fine-tuning. See, historically, if a robot learned to pick up a box in the simulator, you still needed hours or even days of real-world trials to account for physics differences, latency, sensor noise.
The gap between the virtual and the real.
Right. With improved zero-shot transfer, those physics models are so accurate that the simulated skill translates almost perfectly to the real hardware. That leap across the sim-to-real gap is what makes large-scale deployment economically viable. You train once in the cloud and deploy thousands of working skills simultaneously.
That simulation capability feeds directly into a really fascinating academic achievement this week from MIT, their speech-to-reality system. This system bridges natural language, digital design, and physical fabrication. And the implementation is genuinely revolutionary. A robot can translate a spoken command. You literally say, I want a simple stool with 3 legs and a slightly curved top, into a finished, assembled physical object in minutes.
This is so much more than just a 3D printer hooked up to a voice assistant. This represents a new, flexible manufacturing paradigm. It's almost like material programming. The technical pipeline is incredibly sophisticated, and it shows the complete end-to-end integration we keep talking about. It starts with an LLM parsing the spoken command to understand not just the words, but the intent and the required geometry. That command then feeds into a 3D generative AI model that designs the object based on the robot's physical constraints and the available material palette. That design then goes through a rapid physical viability check. An algorithm confirms it won't collapse, be unbalanced, or violate structural integrity rules.
Only then does it actually get built.
Only then does the robotic arm receive the detailed path planning and assembly instructions.
And the material implication here is as important as the AI. They're using these modular blocks.
Exactly. What really stands out is the environmental implication, the circular economy component. The objects are constructed from modular blocks connected by electromagnets or simple snap-together systems. This means the robot can easily disassemble the object and reconfigure the materials into something entirely new.
So it could turn that stool back into blocks.
Right. It could turn that 3-legged stool back into blocks to build a storage shelf an hour later. This isn't just flexible manufacturing, it introduces a true circular economy model to physical fabrication, where raw materials are never waste, but always resources ready to be recompiled on demand. It basically eliminates the concept of dedicated inventory.
Okay, so we've covered the financial capital and we've covered the cognitive software, which is clearly winning the valuation war. Now let's get into the metal, the plastic, the polymers,
Hmm.
the hardware itself. We are seeing a profound fracturing in design philosophy, what we're calling the Great Divide. On one side, you have rugged industrial utility, prioritizing pure strength and durability, and on the other, biomimicry and human-like softness, prioritizing compliance and safety. Let's start with the doctrine of robustness. This is exemplified by the Chinese startup Engine AI's T800. This machine clearly prioritizes durability, dynamic stability, and brute power above all else. The most compelling, if slightly terrifying, demonstration of the week was that viral video where the T800 physically delivered a controlled kick to its own CEO,
Right.
just to dispel rumors that the impressive movement demos were CGI fakery.
That kick was not just some aggressive marketing ploy. It was a highly specific, complex control problem being solved in real time. It demonstrated extremely high dynamic stability and robustness. For a robot to deliver a high-velocity, high-impact kick, it has to instantaneously shift its center of mass to a single support leg, manage these massive reactionary forces, and then recover its balance to a stable stance without falling over.
And do it in a fraction of a second.
In milliseconds. It requires high bandwidth feedback loops and precise torque control on every single joint. This machine is built to compete in the most demanding industrial environments. It stands 1.73 meters tall, weighs 75 kilograms, and the T800 boasts high torque actuators delivering a massive 450 newton meters of torque in its key joints.
Which is a lot.
For context, that rivals the output of some smaller, dedicated hydraulic systems, but delivered through a cleaner, all-electric architecture. That means it can lift heavy pallets, handle high-inertia tasks, and resist external forces far better than its lighter competitors. And critically, it uses a solid-state battery, which increases safety in industrial settings and allows for a substantial 4 to 5 hours of continuous runtime, a non-negotiable metric for integration into factory shifts. This robot is sending a clear message. It is designed for heavy-duty work.
Okay, so now let's contrast that ruggedness and brute force approach with the anthropomorphic soft robot approach. This is being led by EV manufacturer XPeng and their iron humanoid. XPeng is all about emphasizing biomimicry, compliance, and soft actuation.
The iron is a masterclass in modern materials science and mechanical design. Instead of relying purely on rigid metal linkages, heavy gearboxes, and large motors, which are inherently stiff, it uses advanced DLP 3D printed lattice structures within the limbs and joints.
Lattices, so like a honeycomb pattern.
Exactly. Complex honeycomb patterns printed from compliant polymers that simulate human muscle groups. And why does this matter? It means the robot's joints are inherently compliant. They have variable stiffness and damping, meaning they can absorb shocks, flex, and yield, much like biological tissue. This makes the iron inherently safer and softer to be around humans. If it accidentally bumps a person, it interacts without the risk of that crushing, rigid force associated with high-torque, traditional robotic systems. It's designed to replicate the passive dynamics of human muscle and tendons, aiming for high energy efficiency and non-threatening interaction in environments like retail, customer service, or even elderly care.
The compliance argument is compelling, but we have to address the major design controversies surrounding the iron. It has a distinctly gendered appearance, with a body form factor that includes breasts and wide hips. XPeng's CEO defended this, saying it fosters emotional connection and trust in consumer-facing roles. As an expert, what do you make of that controversial design decision?
Well, this brings up the uncomfortable uncanny valley problem in psychological robotics head-on. There is a deep divergence in design philosophy here. Should a robot look like an efficient functional machine, like the Engine AI T800, or a synthetic human, like XPeng's iron? The uncanny valley is that dip in affinity that happens when a robot looks almost human, but not quite, and it causes revulsion or distrust. XPeng is clearly betting that by pushing the anthropomorphism fully, even including these gendered features, they can move past the uncanny valley. They're trying to cultivate a sense of familiarity, trust, and acceptance necessary for long-term domestic or service integration.
So they're leaning into it.
They are. Their defense centers on the idea that humans instinctively use psychological cues like body language and gender representation to gauge safety and compliance. It just highlights that modern robotics is increasingly grappling with social engineering and psychology, not just mechanical hardware. It's a fascinating, if divisive, choice.
Before we move on, we have to touch on the third design philosophy, the specialist approach. This is embodied by Weave Robotics Isaac. This robot completely eschews the general-purpose ambition that Skilled and NVIDIA are striving for. It chooses instead to master one notoriously difficult task: folding laundry.
This is a shrewd, market-driven design strategy. It acknowledges the immediate, painful limitations of general-purpose AI. While foundation models are getting vastly better, end-to-end reliability for everything, driving, cooking, organizing, folding, that's still years away. So Isaac focuses its entire design, its vision system, and its manipulation suite on the single, repetitive, and time-consuming domestic chore.
And folding is surprisingly hard for a robot.
The manipulation challenges are immense. You're dealing with varying fabric textures, rigid versus compliant materials, the need for precision kinematics. By focusing solely here, they can deliver 99% reliability on one task right now. Their economic model is also unique and deserves attention. They're positioning Isaac as a luxury, entry-level appliance with a high price point, $59,000, with a significant deposit required. It's a clear Tesla-like strategy for the home market. They are deliberately funding their expensive R&D through high-net-worth early adopters to establish a robust manufacturing and service base.
So the first buyers pay for the development.
Exactly. This allows them to drive down costs for eventual mass market deployment 5 to 10 years from now. They're effectively monetizing domestic utility right now rather than waiting for universal intelligence to arrive.
And as we move into our final sections, covering the reality checks and ethical implications of all this, if you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and keeps us bringing you these deep dives. We've talked a lot about the incredible progress in commercialization and cognition, the deployment deals, the $14 billion valuation, but now we need to pivot sharply to the reality check. Because current AI autonomy, particularly in high-stakes public settings, is still limited. Which brings us to the industry's Wizard of Oz problem. And the starkest, most viral reminder of this limitation was the public failure of a Tesla Optimus robot at a demonstration in Miami. It instantly created a massive, confidence-shattering PR issue.
We really need to analyze this specific incident closely. The video evidence suggests it wasn't a core autonomy failure, but rather a profound illustration of the industry's reliance on human intervention. Just before the Optimus robot dramatically fell backward, it performed a distinct, rapid hand gesture. It mimicked removing a virtual reality headset from its face.
That one movement that exposed everything.
Exactly. The compiled video evidence strongly suggests a teleoperation error. The robot was likely being remotely controlled by a human operator for the demo's high-stakes, unpredictable environment, and when that human operator failed to properly disengage the control link before removing their VR headset, the robot, faithfully mirroring the human's movement, shifted its weight, lost its balance, and collapsed. This is the Wizard of Oz problem. Presenting something as fully autonomous when it still relies heavily on human teleoperation for data collection, for safety assurance, or for risk mitigation in these high-profile settings.
So is this simply deception, or is this just a necessary phase of development? Because it feels like a dangerous discrepancy between public perception and physical reality.
It's a necessary but poorly managed phase. Look, robotics researchers use teleoperation for two critical reasons. First, to gather massive amounts of high-quality data, the human shows the robot exactly what to do, which speeds up training. Second, to prevent catastrophic failures during high-profile, high-risk tasks. The problem isn't the method itself, it's the lack of transparency about its use. Trust is the new currency, and events like this erode it immediately. It reminds the public that these humanoids are still just puppets until the underlying AI can truly manage unforeseen complexities reliably.
On a more positive note regarding the infrastructure necessary for scaling, Unitree addressed the industry fragmentation problem head-on. They launched the world's first humanoid app store for their robot platform. This is a centralized platform designed for sharing, distributing, and downloading robotic skills.
This is huge for the democratization and growth of the robotics ecosystem. It echoes that software OS idea we discussed with Skilled. Instead of every company needing to custom code every tiny movement, how to turn a specific doorknob, how to climb a particular flight of stairs, the Unitary Robotics developer platform acts as a universal action library. Users can upload custom-trained movements. It's basically a form of crowdsourced skill development. For example, if one developer successfully trains a robot to perform a complex welding task with high dexterity, that skill, the trained policy and motion plan, can be instantly downloaded and deployed by every other humanoid running on the Unitary ecosystem.
So you're not reinventing the wheel every time.
Exactly. It addresses the data scarcity problem by making skills instantly scalable and transferable across the entire community, allowing users to specialize in movement design rather than needing to build an entire operating system from scratch.
It's important to maintain perspective here, and remember that the rise of the machines isn't just about humanoids. We also saw significant, if less viral, non-humanoid advances this week that show the broad sweep of robotics and AI integration across other critical fields.
Oh, certainly. Look at space robotics. Stanford's in-orbit AR system, developed for NASA's Astrobee robot currently operating on the International Space Station, it achieved a remarkable 60% speed increase in trajectory planning. The challenge in zero-G is not just movement, but planning movement in highly cluttered, power-limited environments. This demonstrates the immediate, mission-critical role of AI in autonomous space operations where human intervention is impossible or severely delayed.
And we also saw major medical breakthroughs, underscoring the shift to AI-enhanced specialized hardware. Edge Medical Robotics introduced the single-port SP1000 system. This is a game-changer for minimally invasive surgery.
Single. Instead of requiring 4 or 5 small incisions for the various tools and cameras, this system allows complex surgeries to be performed through a single tiny incision. It drastically reduces patient trauma, recovery time, and risk of infection. They completed their first gynecologic clinical trial in China this week, confirming its precision. And what's more, the SP1000 integrates native 5G telesurgery readiness, which is crucial for addressing global healthcare disparities. It allows expert surgeons to operate remotely on patients in underserved, rural regions thousands of miles away.
And finally, we have to discuss the ethical friction that this rapid integration is creating, particularly because uncaged humanoids are sharing unstructured space with us. The IE called for urgent new safety standards for humanoid integration this week, specifically citing the unique proximity risk.
Proximity risk is the obvious one. When you put a 75-kilogram machine with 450 newton-meters of torque next to an ordinary human, the risk of crush injury is real, even if the robot intends no harm. But the IE report highlighted a much more profound psychological risk they termed emotional overtrust. This is far more insidious.
Emotional overtrust.
It occurs because we humans are hardwired to trust things that look like us, especially if they are compliant, like the Xpeng iron. Users assume a robot is inherently safe, intelligent, and capable simply because it looks human.
Which could lead to dangerous behavior.
Exactly. Like reaching into the robot's operating area without confirming it's powered down, or asking it to perform a task far beyond its current programming capability. We are projecting human levels of competence and safety onto these nascent AI systems, and that misplaced trust is a regulatory nightmare.
And this ties directly back to our domestic robots, like Isaac, raising serious questions of data sovereignty.
It does. This is the privacy versus performance trade-off playing out in your living room. To get a robot that learns your routine, folds your laundry perfectly, and knows your preferences, which is the performance promise, you must allow its array of sensors, cameras, LiDAR, microphones into your most private spaces. The question of data sovereignty then arises. Who owns the video footage of your living room? Who owns the detailed point cloud map of your house? And critically, when the machine learning models are trained on that highly intimate domestic data in the cloud, who benefits? Society has yet to decide where that line is drawn, especially when companies rely on that private data to train the next generation of general intelligence models. The ethics of pervasive sensing are hitting home much faster than anyone anticipated.
So what does this all mean for the history of technology? If we step back from the incredible detail of the last, half hour or so, 3 core takeaways define this week in the history of AI and robotics. And they all point to immediate systemic change. First, the transition is complete. Humanoid robotics has decisively moved from a research curiosity to an industrial category. This is evidenced by the massive 10,000-unit deployment deals like the one between 1X and EQT, which fundamentally shifted the financial model to OpEx. And the massive scale of consolidation led by SoftBank acquiring legacy industrial power. The machines are being manufactured and shipped, not just prototyped. Second, the software battle is paramount. The core competitive advantage now resides in the brain. The foundation model, whether it's Skilled's $14 billion universal brain or NVIDIA's advanced ThingAct framework with its visual plan latent, that is what's defining the OS for robotics. Hardware is merely the physical endpoint for that intelligence. And finally, the reality factor. Trust is the new currency. The industry must urgently navigate the precarious line between genuine autonomy and the reliance on the Wizard of Oz teleoperation method, especially in public demonstrations. Credibility will determine the speed of integration moving forward, particularly as we grapple with risks like emotional overtrust.
The machines have risen, now they must get to work. And, considering the rapid maturation of the hardware, demonstrated by the sheer robustness of the Engine AI T800 and the compliant soft actuation of the Xpeng Iron, and the sheer scale of deployment driven by new financial instruments like that EQT portfolio model, the core challenge now shifts fundamentally. It is no longer a question of if we can build the robot, it's a question of managing the infrastructure for its integration. And this includes securing the physical supply chains and manufacturing capacity to keep up with demand, but even more importantly, managing the ethical, psychological, and regulatory frameworks governing human-machine coexistence. We must decide if we are truly prepared for this level of integration into our factories, our logistics networks, and yes, our homes. That conversation, catalyzed by the events of this single week, is only just beginning.
We love hearing your thoughts. Whether you're watching Tomorrow Unveiled on YouTube or listening on your favorite podcast app, leave a comment and let us know what you think about the shift to massive commercial robotics deployment. What stands out to you about the future unveiled this week? And if you haven't yet, please leave us a rating and review for Tomorrow Unveiled. It makes a huge difference. Thanks for diving deep with us. We'll see you next time.